I'm pleased to welcome Dennis Lettenmaier to the podcast. Dennis is a distinguished emeritus professor in the Department of Geography and Civil Engineering at UCLA and joined the faculty there in 2014. Prior to this time, Dennis was a professor at the University of Washington from 1976. So Dennis has covered a wide range of topics during his career, and so it's kind of hard to focus on different things, but mostly hydrologic modeling and prediction, remote sensing, hydroclimate, and water management. So today I think we're going to talk a bit about the Colorado River Basin, his work there, importance of snow in the Western U.S., flooding trends, and then some general issues related to modeling and remote sensing. So we may not get to everything, but that's the idea anyway. Thank you so much, Dennis, for joining me.
Well, thank you for having me.
So Dennis, I think it would be good to start off with the Colorado River Basin work, and because the regulations is being re-adjudicated or renegotiated in this year, and so there's a lot of interest in the declines in stores that we've seen over the past couple of decades. And so you did some early work there, and you talk about different droughts in the mid-1900s and also more recent droughts, and emphasized the importance of temperature in the post-2000 droughts. And also your work with Vic there, you show, which sub-basins really contribute most of the flow in the upper basin. So it's a very nice analysis. Maybe you kind of could describe it just briefly.
Sure. So I think the work mostly in the Colorado River goes back to a 2004 paper. That was part of something of a group of projects called Accelerated Climate Prediction Initiative, which the late Tim Barnett, then at Scripps, had convinced DOE to fund. And so there were three major river basins across the West: the Columbia, Sacramento, San Joaquin, and the Colorado. Interesting side note to that is that Tim got the money to do this, came around, wanted us to do some modeling, and we've been working on big model applications, especially in the Columbia. And he wanted done in three major river basins, asked me for a budget. I put the budget together, and he called me up and said, well, we don't have that much money. You're going to have to cut something. So I said, okay, well, we'll cut out the Colorado River. We'll only do. So what ended up happening is a couple of months later, Nicholas Christensen, who's a master's student, came into my office and he needed a PhD topic. And I said, well, you know what? We already outlined what we would do in the Colorado. Why don't you do that? So we ended up doing it anyway. And that first work is Christensen et al., 2004. I think it's climatic change. That's gotten a fair amount of attention. But Nicholas put together, and we've done this a number of other places, the Vic model to model the hydrology, but he also built a simple reservoir model of the system. And we had a little bit of experience by then in dealing with reservoirs, because it's one thing to go simulate the hydrology, but the storage in Lakes Powell and Meade is 4 times the mean annual flow of the river. So everything's about water management, right? Just saying this is what the hydrology is going to be, that's half of it. The Bureau, of course, has a model of the system. It was very clunky and basically impossible to get your hands on. Would have had to have been run on their computers and so on. And like many of these other things, there's certain parts of it are kind of hardwired to the historic climate. So he put together a model that kind of reproduced the main aspects of the Bureau's model, but then was able to explore things like how power generation would fare, water deliveries for irrigation especially, and water deliveries to Mexico. So we looked at both of those. At that time, my recollection is the climate projections, and that's really what the project was all about. How was the climate going to affect all of this, were coming from CMIP 3. And it turned out that was the third IPCC assessment, and the climate models were run for that. There's a whole bunch of downscaling and other parts of this that go along with it. But the bottom line kind of was that group of models was quite dry across the sort of lower mid latitudes. And there was a lot of differences in how much the precipitation would decline. Our numbers, if I recall correctly, actually were towards the low end of the declines. In other words, less negative than what various other people. Some of this had to do with the downscaling, and there's a whole bunch of discussions and meetings and so on after that. Some of this got into Julie Vano wrote a BAMS paper on reconciling different projections for the Colorado River and why they were and so on and so on. That came about, I think, about 10 years later. But we did do that first study. A little later along came the fourth IPCC, which was CMIP 5, if I have this correct. And the projections were for the drying to be less over the Colorado River Basin. There was a second paper in 2007 kind of did an update. Now, I may have the projections a little bit mixed up there, but basically what happened was kind of interesting. I was on an academy panel whose primary charge was to try to reconcile different tree ring records, because there had been a lot of work done in trying to reconstruct long-term flows, pre-instrumental flows of the Colorado River. But there was a part of that having to do with the instrumental record. The long and the short of it is, I wrote a section for the Academy report, and I had Nicholas was still around, asked him to go run the new climate projections. We put the thing in there, and I was told, well, the thing is with Academy reports, you can't have new work that hasn't been reviewed. This hasn't been reviewed, so we're gonna have to take it all out. So what we did, I don't think I'd ever published in HES before, but Hydraulic Earth System Science, the EGU journal, at that time, they produced a pre-review copy. I think it was called Discussions. I'm sure you're familiar with this. You probably had papers in there as well. The discussions papers look exactly like a printed paper. So, and they do it, at that time, they did it in about 2 weeks. So this thing, we submitted it turned up as discussion. So then we cited it as a discussions paper, and they put it in the Academy report. I think the date on that was 2006. 2007, the review comments came back and so on, which weren't that substantial, and that was the permanent version of the paper. So those two papers both looked at what the hydrology changing. And even, the one thing that kind of settled out of all of this is that the sensitivity in fractional change in runoff divided by fractional change in precipitation, which is what in the annual basis, that number is about 2 for the Colorado Basin as a whole. So basically, if you don't know anything else, if you got a 6% decline in the precipitation, you're going to have a 12% decline in the runoff. It's that sort of thing. And we looked at that also. There was a lot of consternation in the change between CMIP 3 and CMIP 5. And CMIP 5, I never quite understood why there was no CMIP 4. Okay. There was only CMIP 3, 5, 6, and now they're working on 7. But that change was fairly substantial, and I think there was kind of a sigh of relief that, okay, things aren't really going to be as bad as we think. But that got into a lot more discussion of, you know, temperature sensitivities as well as precipitation sensitivities. And that's carried on into some of the more recent.
Right, right. And I mean, the Colorado is really fascinating. And somebody was suggesting to me recently, I've listened to a couple of books. I can't read books anymore, it takes too much time. But I was listening to a book by Kevin Fedarko called The Emerald Mile, and he talks
No, I
about,
know it. I've read the book. Yeah, I actually read them, and I don't like listening. But yeah, that is a fascinating book.
yeah, yeah. When I always have a book that I'm reading and a book that I'm listening to, but uh, and he described Kenton Grua and going down the Colorado in a
Yeah,
dory,
this was 83, right?
Yes, yes,
Yeah.
yes. And so I guess there was so much flooding and that they made releases to Powell through the dam there and so really high flows and they made it down in about 37
Oh, it was
hours.
some remarkable time. But there's a lot of other stuff in the book about the sort of spillway issues and cavitation.
Oh
And,
yeah.
reportedly there were chunks of concrete coming out of the spillway the size of a Volkswagen and so on. I mean, depending on who you listen to, it's, oh yeah, it wasn't really that big a problem, or, they almost lost the dam. But certainly they had not had since Powell um, began to fill, and I can't remember, was that 70s maybe? I mean, because the storage is double the flow of the river at that point. It takes a long, long time to fill it. They hadn't seen anything like that level of inflows. And the other side story is very interesting is that the forecasts really of the inflows were really a bust, because what happened is there were some very substantial late season snow that is very abnormal, and the forecast models basically were all typically they regress on April 1 snowpack. And those regressions showed, yeah, I mean, it was a little bit above average, but it wasn't anything substantial. But then there's all this extra snow that the forecast models didn't know about. So that's all kind of the backdrop of the book, which is pretty
Right,
fascinating.
right. And I guess 83, if you look at the flow at Lee's Ferry, I mean, 83, that period was extremely high, probably the highest, some of the highest on record, probably similar to, when the compact was formed in the early 1900s, as high as those
Yeah,
flows.
yeah,
So anyway, if people are interested, that's and Kevin goes into a lot of detail about the dam and the Bureau of Reclamation and all of that. And you mentioned them earlier in their model, and also Vicky, the variable infiltration capacity model that you guys developed. So that's excellent. So there've been a couple of papers out recently. Yeah, Chris Milley's paper on the importance of temperature and increased evapotranspiration in the Colorado River Basin and Clausius Clapeyron equation. With the increasing ET and what that would do to stream flow. And then Marty Hurling seems to take a kind of maybe a different viewpoint and saying that, suggesting that, maybe we will have some wet periods like we've seen in the past, and that we will have high stream flow potentially sometimes. And his bounding estimates, minus 25 to plus 40% in the future. And he mentioned that if he does his modeling and conditions it on the current drought from about 2000 to the present, that there's an increased likelihood of a wet period occurring in the future. So I'd really like to get your thoughts on those two viewpoints, importance of temperature and evapotranspiration versus likelihood of getting, El Nino, and would that be swamped by the ET, or everything is so dominated, as you said, by snow in the upper basin. So, how are those things going to pan out?
So the hurling, let me go back a little bit, because there's an history backdrop to Marty's work on the Colorado River, which perhaps isn't as well known. there was a paper of his early 2000 sometime in a regional journal that doesn't exist anymore, but it was published down at the University of Arizona. And in that paper, they put together a very simple hydrologic model of the Colorado. This was the hydrology only, no water management. And I don't remember which set of GCM scenarios they were using, but they concluded that the flow of the river over the next century was likely to decline by 50%. A lot of people said, including myself, said we don't believe it. There were actually a series of meetings to try to figure out what was going on. And some of the backdrop was this whole business of reconciling all of these different estimates, which showed up eventually in 2010-12 in this Julie Vano et al. Paper. But it turned out that the major issue there was the very simple model they had was a very crude spatial scale model, which did not represent the effects of snow at high elevation. And rather obviously, if you average snowpack over the entire basin, and you take an average elevation and you figure out what's going to happen, the snow's all going to disappear because it's not cold enough anymore, then you're not representing the high elevation snow. So Marty kind of disavowed that model and moved on to something else. The paper you mentioned, and I think they get sensitivities that are to us very low to temperature. They have numbers, if I remember correctly, are kind of like 2, 4 or something percent per degree C. The Millie paper gets about 10 using a combination of satellite data for the radiation and some modeling for snow cover and so on. We typically have been getting numbers in both Julie Vano's work and more recent work by a student, Mu Zhao, who wrote a paper, something on the causes of declining Colorado River stream flows or something that might have been about 2018, WRR paper. We typically with Vic model have been getting about 5% or a little more than half of what Chris got. So there's kind of two things. One, the Millie paper, Millie and Dunn paper, the Science one 2020, I think is really a seminal work because it shows the reason for the declines on a physical basis. And it all distills down to something that's actually pretty simple, that most of it has to do with contrast in albedo at high elevations with warming for the period when in the warmer climate there's no snow and in the cooler climate there is. That period is like a matter of weeks, but it happens at the time when solar radiation is the highest because you're at or near the vernal equinox. And that kind of extra net solar radiation gets converted into evaporation. And by difference, aside to absent precipitation changes, that difference comes out of the flow of the river, right? So that's where he gets the number. So what's kind of interesting as an aside, my student, Zaux Bond, wrote a paper looking at the so-called Millie mechanism across the entire West to see where it was greatest and so on. And it shows it mostly is maximized over the Colorado River area, probably in part at least because it's fairly far south in terms of where hence the solar radiation is higher. But there's a bunch of stuff in that paper, but we kind of put in almost as an afterthought, buried in the paper is an analysis trying to understand the reason why we get 5% and Chris gets 9% or so. And there's a whole bunch of differences in models, methodology, and all the rest. But what about half of that difference distills down to is changes in net long wave radiation. And it's kind of interesting because, in terms of net radiation that melts snow, you think solar is obviously going to be the big number. Solar isn't really affected by climate change, not directly that much. I mean, there's transmissivity of the atmosphere, which changes and so on and so on. But in the overall scheme of things, that's uh, somewhat minor. What happens is in all the simulations we've been doing, for our simulation of long wave, basically we just increase all the temperatures. And if you do that, you're taking differences of absolute temperature to the fourth power. So what happens if you increase that? You kind of got an effective temperature of the atmosphere and an effective surface temperature. Well, a whole bunch of subtleties and details aside, if the atmospheric temperature and the surface temperature increase by the same amount, you increase them both, the net or the downward component of the long wave actually goes down. Or the effect of the difference, you get the differential long wave goes down. But in a warming world, you've got increased water vapor and increased CO2, which actually increase the atmospheric emitted. When you accounted for that effect, it flips the sign of the change in long wave so that the net long wave is actually increasing instead of decreasing. And I think by accounting for that, Zalkson ran some simulations and we were getting numbers more like 7% or so. It doesn't close all the difference, and there's a bunch of methodological things, but it's kind of interesting. We since then have looked at this in the reanalysis, the ECMWF Era 5 reanalysis, and it appears that the trend for downward long wave in the reanalysis is actually negative. We're going to look at that a little bit more carefully. So do they not have the CO2 and water vapor effect in the reanalysis? I'm not quite sure. There's something interesting to look at there.
Well, I think, it's healthy to have these different viewpoints because it forces us to think about what's going on and then to question different things, so it's nice.
Well, and also the basic physics. We never really thought that much because long wave is a fairly small part of net radiation in the springtime to worry about. Then we realized, that warming signal in the atmosphere isn't in there. And he does in Chris's work, it's there because he's getting the long wave and the short wave out of some Ceres satellite products.
Okay.
So arguably it's observations. And it is kind of interesting that over 20 or 30 years, that is enough to go cause, a few, I believe 10 or so watts per square meter, which is not negligible.
Right, right. So, I mean, you mentioned earlier that the 83 flooding and, and the discharges from Powell and stuff related to late season snow that they missed in the forecasting. So, could we possibly get, some events like that again? And if we got those events, would we get high stream flow? I mean, it seems to be a lot of uncertainty. I realize that temperature is much more a robust parameter to predict in the future and all that sort of thing. But, there's a lot of uncertainty and all sorts of things going on. So, I mean, it seemed like we could potentially get some wet years or.
Well, yes. I mean, it would not surprise me terribly if over the next 10 or 20 years, we saw some kind of shift and you started getting some big precipitation years. I mean, the climate models are notoriously uncertain in precipitation. Where everything lines up, the observations and the climate models is warming. There's differences in how much, but
Right.
it's pretty clear it's been happening it's been happening, especially across the West, and it's quite likely that'll continue. That we have reasonable understanding of, but precipitation, pretty uncertain. A lot of decadal scale variability. You mentioned that wet years in the early 80s, a series of them, and
Hmm.
then certainly back in the 1900 to 1920 Colorado River Compact years. Is it certain we're never going to see that again? I certainly wouldn't go out on a limb and say that.
Right, right. So, Dennis, you've done a lot of work on snow, and the snow is hugely important. I mean, the Upper Colorado River Basin provides about 80% of the water for the entire Colorado Basin, and snow is a primary driver. So, you mentioned, you've looked at it in the Sierras, and we often hear in California, the governor going out April 1, what's the snow like, and all of that sort of thing. Um, so you have described some of that in your work, decreasing snow and losing that reservoir storage that we get from snow, and then importance of rain on snow. Maybe you can describe that a little bit, Dennis, and the importance of snow in the Western U.S. for many of these basins.
Yeah, well, as an aside, there's a paper written by Dong-Yu Lee, maybe late 2017, 18 timeframe. Dong-Yu was a postdoc who worked for Steve Margulis in civil engineering and myself. And I had suggested to him that he might, this was when he was still a student at Ohio State, that if he was looking for something to do, might see if he could develop some sort of algorithm which gave us some real basis for understanding how much of the runoff in the Western U.S. comes from snowpack. And the side story on this is that lots of people waved their arms and said how important it was, and there even were some numbers in some papers that were basically made up, and then those papers got cited as the source, right? And we were guilty of this ourselves because it's the kind of thing in the introduction to your paper you say how important it is, right? So Dong-Yu went in and for the Vic model, put a tracker on it to go see in the model world where the water was coming from, how much originated as snow. And I mean, there's a map in that paper that's been fairly widely used. So at least for that model, we now have some numbers. And not surprisingly, aside from the coastal drainage areas where it doesn't amount to much, for the Sierras, Cascades, and so on, it's numbers that go up in the probably 60+% range. And if you go to the interior of the West, even higher, up to 80% in some of the colder areas. So, it's a big deal. And for water management, um, you know, you assuming the precipitation doesn't change, you still got the precipitation, but the water is going under the bridge earlier in the year. And that's actually happening. There's a paper by Ira Stewart, who was a PhD student of Dan Kahan's in early 2000s or so. I think it's 2005. I've used a figure out of that paper in many talks because it basically just shows the change in timing and that's been advancing earlier in the year over the last half century or
Yeah,
so.
so I mean, I guess you're right. I mean, that would be critical for water management because the reservoir storage then that they have is not enough maybe to store it to keep it for later in the summer than when you have dry periods in California and Central Valley and other regions like
Yeah,
that.
that is the challenge. And, it's interesting. Right now, we're in a basically what people call snow drought across the West. The snowpack is way low. I mean, I was at a meeting last week in Salt Lake City, and basically the Wasatch rains, there's hardly any snow on it. Similarly, in the Cascades, so there's I occasionally read the comments to articles in the Seattle Times, and there was there was a discussion. Well, I mean, they had some very warm temperatures last week, and yeah, this is great, but I mean, we got we got no snowpack. What's that going to mean? And somebody was commenting, well, the Yakima River reservoirs are way above average. And, you know, they have big floods up there in December, and that took whatever early snowpack there was off. They got they got some cooler storms, but then there was another warm period, and so there's not much snowpack. So the interesting question is, the water's in the reservoirs that should have been in the snowpack, right? But what happens? Well, the problem is, unless there's a big shift, which could happen, but they're kind of running out of time, because by the time you get to about early March, you're not getting much snow accumulation anymore. So realistically, there's about another month. There'd have to be a bunch of cold, very high precipitation storms, which it doesn't look like is going to happen. So what's going to happen is that the reservoirs will be full or close to it early on, but they won't, you know, they begin to start irrigating in April, and generally you've got inflows from snowpack continuing on into like June or something. Yakima River system is fairly low elevation. The higher elevation stuff in the Columbia, the peak flows are actually in July, right? They're not going to get that. They're not going to get that flow, and it's going to be it's a big water management problem. It's better than the years where the drought is a warm, dry drought, so that you just didn't have the precipitation at all. But it's certainly way worse than the normal situation.
Right, right. And you've done some work on, so if the snow is decreasing, then rain on snow and its linkage to extreme flooding or whatever. I mean, can you describe that a little bit, Dennis?
Yeah, the rain on snow thing is kind of interesting, because this is one of the sort of, the climate community likes to think that, flooding is going to be worse. It actually turns out, and the same postdoc, Dongyu Lee, has a paper on rain on snow events across the U.S. and their sensitivity to warming. In coastal mountain maritime heading streams, like those from the Sierra and the Cascades, generally rain on snow floods go down with warming. And the reason is less antecedent snow. Okay, in order to have rain on snow, you have to have snow, but if it warms up, you end up a lot of that lower elevation snowpack. There's no snowpack there in the warmer scenario. The places where you get more is the colder regions of the interior of the West. And there's a figure in his paper that shows that pretty clearly. The places where they show some increases or high elevations in the interior. In observations, we wrote a paper. It actually started as a class project in my graduate class. Huilin Wang is the first author. Maybe it's a 2022 or 3 paper in GRL. Looks at changes in flooding across the Western U.S., and they do a classification into different categories, and they split things up. In the interior of the West, you tend to get snowmelt floods. The peak floods mostly come from warm temperatures in the spring. This would be streams draining the Rockies and so on. In the coastal West, most of them are associated with atmospheric rivers. That's one of the partitionings, but they partition out rain on snow events as separate from the others, and it's based on how much antecedent snowpack and so on. And then there's a monsoon category down in the Southwest and so on. Turns out that the only statistically significant changes in any of the categories is the rain on snow events, which have been decreasing, and they're predominant in the coastal river basins, and it's for exactly the reason I just described. We
Hmm.
surmise that less snow is led to in a general warming. There's a little bit of an increase. There's not very many stations where this dominant mechanism, but in the interior where convective storms, where they tend to get summertime convection, can lead to at least some of the major floods. That's actually seems to have gone up a little bit. Everything else, there's nothing statistically significant going on.
Right.
Um,
Well, I really appreciate that you guys look at the data in detail. Oftentimes we kind of make these logic jumps, oh, well, this is happening and this is happening, ergo, this is going to happen. And then people forget to look at the data. Well, what has been happening? And so
well,
it's very important.
a lot of this stuff is more complicated than it seems at first. And even the snow stuff. When we started on this back with this EPA report to Congress in the late 80s, you know, the the details have all changed, but the big picture was warming, less snow, change in the seasonality, right? And there have been a gazillion other studies done since then. And in the West, I mean, that's basically the result you get. But there's a whole lot of fine points that kind of get buried in that. And there's a really interesting paper by Keith Musselman at NCAR a few years back, which is the title is something like Slower Melt in a Warmer Climate. And the first thing is slower melt in a warmer climate. What do you mean? Well, the reason is that as things warm up, snowpacks move earlier in the year and you've got less available radiation to melt. So the melt rates tend to go down. And I mean, he shows this from very detailed analysis of a whole bunch of observations at snowtel sites and so on. So there's other things that that kind of go on
Right.
in a warming climate. The other one that we wrote, Saux and Bond's last dissertation paper, is something like decelerating rate of change in Western U.S. streamflow or something like that. And it's like decelerating rate of change. Well, it's fairly obvious when you think about it, because as the snow slowly goes away as you warm up, there's less and less of it there. So there's less to be impacted by warming. And so the rate of change uh,
Hmm.
tends to go down in ET runoff and so on and so on. So
Right.
it's a little more complicated than is often made to to
Yeah.
seem. I think in the realm of flooding, it's kind of analogous to the temperature. What do we know and what don't we know? Well, you expect precipitation extremes would change. There's a lot
Hmm.
of complexity there, but just because water holding capacity of the
Hmm.
atmosphere going up, that more water in the atmosphere, and if it gets tripped off, you could get higher uh, higher
Hmm.
extremes. And there's some evidence of this happening in the observational record.
Hmm. Hmm.
Okay, that, we'd done an analysis that was never published, but of 1,000 stations or something across the conterminous U.S. And it was something like at 5% significance level, there were significant trends in about 10% of the stations in the extremes, the annual maximum precipitation, I can't remember what duration, and about two-thirds of those were upward. We also did some work looking at major urban areas a few years ago, and there seemed to be increasing changes. But in the floods, we're not picking it up. And so
Right. I
the
think
interesting
maybe.
question is why not?
Right.
Um,
Before we move to the flooding, I would like to just mention a little bit that, I really liked your paper on the 2023 snow deluge in California. And you
well,
did a nice.
first up, I have to correct you. That was Adrienne Marshall's paper, and she kindly invited me on board basically as a co-author because there's some VIX simulations, and I think they were some ones that we had archived or something. So
Okay.
she did all the heavy lifting on that paper was Adrienne's, but I do think it's a very interesting paper.
And
And
it's a really nice, I love one of the graphs in there, where you talk about, wetter and cooler and look at the different periods and, so much emphasis on drought periods. I mean, I've memorized droughts in different regions, but we don't talk as much about the wet periods. And I think that was a really nice analysis. And 2023 snow deluge, is that linked, do you think, I presume that's linked to the atmospheric rivers too, at that period?
well, there were certainly a bunch of very, very strong atmospheric rivers contributed to that very
Right.
high. What's interesting is because you mentioned that paper, I went back to look at it because I didn't remember exactly what was there. And there's an interesting figure in there where she flags, I think a total of 5 of these years in the record. And the most recent one prior to 2023 is, I guess, is it 83? I think it's 83 was the one also the same year as the Colorado River event that
Hmm.
you'd mentioned. So it's been 40 years, but the earlier ones are all separated by more or less 10 years or something.
Hmm.
So that's not a statistical analysis, but it does kind of suggest they're not happening as often. And she does an analysis with future climate runs and so on, and shows that you'd expect the probabilities, the return periods of these things go up in a warmer climate. But you're not going to see as many of them, but it doesn't mean you're not going to see any of them.
Right, right. And another paper that I really liked was, if precipitation extremes are increasing, why aren't floods?
Yeah.
So, uh,
So the backdrop for that, my main contribution to that paper is that I made up the title. The lead author is Ashish Sharma. The second author is Conrad Wasco. Conrad Wasco, I was the external examiner on his committee. I think it's University of New South Wales in Australia. Um, and he did, I think, the best job of addressing this. There's a whole series of papers now about almost 10 years ago from his dissertation, but basically positing different reasons why. The climate community will wave their arms and say because of increased water holding capacity, the atmosphere, more extreme precipitation, because of more extreme precipitation, more floods. But those of us in hydrology know, and I actually have a visual in some or other talk, what causes a flood. All right. Well, extreme precipitation or melt, if it's a snowmelt driven, right?
mhm,
Obviously increased extreme water supply. But there's a bunch of other things. A big one is antecedent soil moisture, right? I mean,
mhm.
everybody in hydrology sort of knows that. I have a figure also, and I can't remember the author of the paper. I came across it somewhere where they had conditioned, I think they used model, soil moisture from the Vic model, but observed flood extremes by regions, I think across the conterminous U.S. And then they just plotted the fraction of the upper some percentile, 1 percentile or something, precipitation that led to upper something or other percentile floods. And they categorized them by wet and dry soils. It's just a bar plot. In fact, I think I replotted it as a bar plot. They had it some other way. But, not surprisingly, the bars are way higher for the wet antecedent condition. So what Conrad said was that, well, in a warming climate, you're going to get enhanced evaporation. What's that going to do to antecedent soil moisture? Well, you expect it's going to make it drier. So
Mhm.
wouldn't that lead to, you know, decreasing effects? One of these, like many of these things, there's more than just, you know, one aspect of it. He also hypothesized for some Australian conditions, warm season precipitation, which is not what we have in Western U.S., but that the scale of storms, uh, well, the intensity, the maximum intensity appeared to be going up. And he has some observations to show this, that the spatial scale is going down. And so now, depending on how big your river basin is, you may have some parts of it have got
Mhm.
enhanced precipitation, but much of it may have reduced. So, and there's some other some other things potentially go on in there that we don't, uh, you
Right,
know,
right.
we haven't entirely sorted out.
But I think it's great that you ground it with data and you look at the data, and it's very easy to make the logic steps, increase precipitation extremes, increasing flooding, that's easy to think of. But I mean, to look at the data then and really examine it and then evaluate the processes that feed into
Yeah.
it. But most of us we just can't think of more than one thing. And so
Well, the other thing that goes against this, and I kind of ran and railed against this because, I can afford to. I don't have to publish any more than I want in any place I don't want to. But the so-called high impact journals want to see big splash type of stuff. So, a paper that shows extreme floods increasing is going to get a lot more attention than ones that argues that they aren't. And so we get a certain amount of this stuff that is a little bit of selective processing.
right, right. Well, we have to. I mean, people have to sensationalize stuff to get them in those high impact journals. It seems like, and I
Yes.
guess So one was the precipitation extremes. The other was increases in temperature do not translate to increased flooding. That was another analysis, and I guess Yin study, was saying. Are some study that you were involved with, global stream flow extremes more likely to be decreasing than increasing with climate change, and flash flooding more likely related to snowmelt processes.
Yeah, well, there's a bunch of aspects of that, and again, that some of this kind of comes into what we know and what we don't know. I mean, I don't want to seem like a climate skeptic saying no, there's no evidence of increased flooding and so on. There are a number of potential reasons for this, but amongst various others, you know, we analyze what's going on, our data at the places where we have it. Where do we have it? We have it where there are stream gauges. Where do they put stream gauges? Well, in general, they don't put very many stream gauges, and certainly not ones with long-term records in small urban basins. But what would you expect in an urban basin with high impervious area? Well, you'd probably expect a stronger connectivity of changes in flooding to changes in precipitation than you would in larger basin with a bunch of these other things going on. And certainly, a parking lot there's no antecedent soil moisture in a parking lot, right? So, but how many gauges do we have that represent those highly urbanized basins? Not very many. The other thing may well be just floods are extreme events. We're looking at extreme precipitation. We're out in the tails of the distribution. The signal may well not have emerged from the noise. Doesn't mean that there isn't something going on there, that when people look at this 50 years from now, it may be more obvious. We don't know that yet.
Right, right. So, Dennis, much of your career you've been involved in various aspects of modeling, and more recently you've been looking at the national water model, and that's promoted by NOAA, and comparing that to what the National Weather Service forecasts are doing. And you've been doing that in California and other regions. Can you maybe briefly describe the National Water Model and, how you feel like it compares with the river
Okay.
forecast centers?
Well, so that's an interesting question. We, developed the VIC model with 30 years of effort into that and so on, done a lot of studies with it. In the more recent past, since I've been at UCLA, we've done several studies where we've tried to go look at different models so that we can avoid potential criticism that, well, is this all model dependent? So in my mind, I mean, the hydrologic core of the national water model, as it were, is NOAA-MP, right? And we've run that in a number of cases. It's sort of interesting. The NOAA comes about from the old NOAA model, which was the land scheme that the National Weather Service used. As nearly as I can tell, the only thing in common between NOAA and NOAA-MP is the name. Okay, they're completely different models. And the old NOAA model was not what I would call hydrologically credible. It focused much more on kind of land atmosphere exchanges than things like runoff production, which it didn't do very well. NOAA-MP, in my mind at least, is hydrologically credible. That's what I would say. And that's one reason that we started doing some work on it. The other reason is that we've been working closely with Marty Ralph's center down at Scripps, Center for Western Weather and Water Extremes, um, and guy named Rob Hartman, who's retired now from the Weather Service, but he was the hydrologist in charge at the Sacramento River Forecast Center for a number of years. So he's been doing a bunch of work with them, and we had some discussions, and I'd asked about National Water Model slash NOAA-MP and why the Weather Service doesn't use that. And Rob is kind of a crusty guy. He just said, well, because it doesn't work. Okay. It's like, well, what do you mean? So that is some of the work that you, by Lu Su, a PhD student of mine, who finished a couple of years ago. I charged her with going off and looking at performance for NOAA-MP. And Rob, through his good graces, because he does have long-term connections with the RFC, was able to get from the Sacramento RFC and the Northwest one access to archive forecasts for actual floods. Okay, so we had the forecast and for Sacramento, we went back 20 years and we looked at a bunch of these coastal basins up and down California and then up in the Pacific Northwest as well. And there's a couple of papers around on this. There's a more recent one by my current soon to finish student on this as well, that with proper calibration and so on, NOAA-MP seems to be comparable, and in some cases does even a little better. I think that there's a lot of not invented here stuff going on. Now, as an aside, at this meeting I was at in Salt Lake City, which was like Colorado River Water Users Group or something like that. A lot of bright people from universities, different agencies, and so on. I was unaware that the whole hydrologic forecasting aspect of the National Weather Service has been reorganized, and somehow the RFCs are now directly connected to this water center down in Alabama. I don't know if they are going to make the shift or not. It will be interesting. It'll be interesting to see.
Mm-hmm. So the last thing I would like to just mention, I mean, Dennis, you use all the data that you can access, and you've been integrating remote sensing into your analysis a lot over your career. And I guess the most recent thing is the SWAT mission and what it does. So maybe you could briefly describe, how you think, and SWAT is soil, water, ocean topography, how that helps with the river discharge and reservoir storage and all of that sort of thing. And your analysis, you've done some analysis in reservoirs and stuff in the U.S., how you think that will advance our understanding.
Yeah, so the connection with SWAT is a long-term one. I spent a year at NASA headquarters in 97, 98. There were a couple of workshops on post-2002 mission planning, where it was post-2002 was because the EOS, Earth Observing Satellites, had been launched by then, and they were looking at a so-called budget wedge and what are we going to do next, basically. So there's a lot of sort of blue sky thinking. And I remember one of those, there were two major workshops, and, kind of what are we going to do about water was one of them. So the soil moisture people were there. That was a pretty strong community there that had been in place for a while. It took them eventually turned into SMAP. Took a couple of tries before that of missions that got canceled and so on and so on. But that was clearly on track. Um, the snow community, frankly, was better organized than the surface water people. Um, but for whatever reason, couldn't quite coalesce on a direction to go. And then there was a whole idea of altimetry. Could we do something with altimetry? So the oceanographers had altimetry since Topex Poseidon. I think the launch in that was 92 or something like that. But that's tracks with very large separation. So there's some work out there that has been used on very large reservoirs, Amazon River and so on. But in order to get anything out of it, you really needed track lengths of like 10 kilometers or so. So it's very big stuff. And the discussion ended up evolving into doing swath altimetry so that rather than having tracks, you would basically have maps. And I won't go into the technology on that, but it turned out as this all evolved, and it took decades, right? I mean, those workshops were 97 and 98, and the launch of SWAT was what, late 2022? So however many decades that ends up being, a bunch. But there was a series of uh, Academy reports, the first decadal review. I was on that in 2000, and the report came out 2007. And that was the first time Earth science had come together to say, okay, what should the priorities be? And there's a whole lot of fine points there we won't go into. But it was clear by then that the oceanographers were interested in swath altimetry because some of the stuff they were doing, well, they got a lot of good science out of the sort of Topex, Jason, and other altimetries. They couldn't get close to the shore, and there were certain other things, small scale eddies and so on. So they had an interest in it as well. So it became clear that if something was going to happen with surface water, it was going to be done jointly with oceanography. So there's another case where my main contribution to the mission was the name. I chaired the part of the Academy committee. There were 7 different sub panels, and the one on water I chaired. And we were a little bit paranoid if we got involved with the oceanographers. They had such a long history that they would push us out of the way. So we wanted a name where the hydrology basically came first. So that's where SWAT came from. So going forward in time, the technology began to solidify. Various other things happened that there were 3 tiers of missions, and SWAT was tier 2, which probably ordinarily wouldn't have gone. But there were some other missions where various things didn't work out and they kind of got pushed off to the side. And there weren't any very major deal breakers on SWAT. Plus, the French put up, I think it was a couple €100 million, which was a big, big thing. I don't think SWAT would have happened. Even although about 80% of what ultimately was spent was U.S., that 20% was really, really important. So to me, the mission having launched is in terms of global hydrology is a huge, huge breakthrough. And we're just starting to get, you mentioned we've looked at some reservoirs in California where we have good storage estimates from in situ and can compare and so on. The thinking is that you probably, for surface water bodies with surface areas greater than about 1 square kilometer, so you can get pretty good data out of it. And this is just starting to come. I mean, there's a lot of details on processing and so on, and evolution of the processing, and it will only get better with time. Lots of discussions with that ongoing now, but it's pretty interesting stuff. So for the storage, reservoir lake storage. And if you try to figure out how much water is stored globally and what are the dynamics of that, what do you have to work with? You basically, you got little pieces of things you can get here and there, but you can't get systematic information. Now we have a chance to have systematic information. For river discharge, lots of effort going into that. It's more complicated than the storage because you basically have to derive, you get the slope gets observed directly and river width. So typically river widths, they're thinking 100 meters, possibly 50. It's in that range. You won't get quality of data or quality of information on river discharge that you would get out of, say, a USGS gauge. But this will also all evolve. Probably it's going to be done with data assimilation into hydrodynamic models, which are already are efforts to go run global scale hydrodynamics and so on. It's only going to get better in time, but it's a huge, huge resource and trips off whole areas of science that we haven't really been able to do too much with in the past.
Right. It must be nice and satisfying to see something that you were involved in a couple of decades ago to come to
Well,
fruition, because most of the stuff we're involved with goes nowhere.
yeah, well, it is interesting because, after the 97, 98 workshops and before the 2007 decadal review, there were some working groups, and there was a working group for, surface water stuff. And you could fit everybody in that working group around a fairly small conference table. Okay, that's what there was in the early days. So to fast forward to some of the more recent SWAT meetings where you got a whole big room filled with, 200 people and so on, and a bunch of people online, it's just a whole different. I mean, the
Right.
interest and so on has exploded, and there's a lot of good work that will come out. It also, I think, somewhat reshapes the whole field. I mean, if you look at um, other fields which have had kind of global scale remote sensing data, atmospheric sciences, and oceanography in particular, hydrology didn't have very much. And now we've got, GRACE, which you've been
Hmm.
very involved in. All
Hmm.
kinds of work has come out of GRACE. SMAP and SMOS, the soil moisture
Hmm.
missions, and now SWAT, and then some others that we get other things out of. The way work in the field is done, certainly on the science, has completely changed.
Right, right. Well, I think we're running out of time, Dennis, and we've only touched a little bit of all of the things that you've been doing. But I really appreciate, it's great that you know the backdrop on a lot of these discussions and how things evolved over time. Because when you read the end result, you don't know how, you know.
That mostly just comes from having been around a long time.
Uh, but I think, the other thing that you and I have in common, we're both soft money researchers, and that keeps
Yeah,
you on your toes.
that does change your outlook. Well, you've been longer than I am, but it was 39 years on soft money at UW. So,
Right, right. But also, you were very involved with the agencies. You spent a stint with the USGS. You spent time at NASA and everything. So you were critically involved in all of those things, and so you had a good knowledge, of what the agencies were thinking, and could feed back into them then to talk about, how things should move forward, sort of.
well, it does broaden your thinking. And for sort of younger scientists who have that opportunity, I was very happy. I was on something called Intergovernmental Personnel Act loan on those two different occasions, USGS and NASA. And that played a big part in my career.
Right, right. And I know at your retirement party recently, there was an army of people around you. So many of your students and everything. And so you have a huge following and you've influenced so many people. But so thank you so much for doing the podcast. Dennis Lettenmaier is a distinguished emeritus professor at the Department of Geography and Civil Engineering at UCLA. And thanks for all your work, Dennis. Really appreciate what you do.
Okay, well, thank you, Bridget, for taking the effort to put these together. It's a big effort. Thank you.